Every senior engineering interview at the top tech companies asks the same question: design Twitter. In 45 minutes, most engineers freeze. Not because they aren't smart, because nobody ever showed them the framework. In the next 18 minutes, I'll give you the exact playbook the candidates who get the offer use. Let's go. Every system design follows the same 5 steps. Step 1, requirements. What are we actually building? Step 2, core entities, the data model. Step 3, API design, how clients talk to the system. Step 4, high-level design, the architecture. Step 5, deep dives, the bottlenecks that make or break it. Same framework, Twitter, Uber, Slack, anything. Let's run it. Every system design interview starts with requirements. The goal: agree on scope with your interviewer and show you can think about the system holistically. Split your requirements into 2 buckets, functional and non-functional. Functional is what the user can do. For Twitter, that's post tweets up to 280 characters, follow other users, i.e., see a home timeline, like and retweet, and search across the platform. Non-functional is what the system promises: 300 million daily active users, 100 to 1 read to write ratio, sub-second timeline latency at the 99th percentile, 4 nines of uptime, and end-to-end encryption for direct messages. State both before you draw a single box. Now, core entities, the data models the system actually stores. 8 entities cover the entire surface area: user, tweet, reply, follow, like, retweet, hashtag, and media. Each entity has its own fields. Take a tweet. It has an author, content, media references, and a timestamp. A follow is directional, one user pointing at another. 2 or 3 entities is usually enough to anchor a design. We have 8 here because Twitter genuinely depends on all of them. Capacity estimation is the step a lot of candidates skip, and that's a mistake. This is where you prove you've actually operated systems at scale, and the numbers here shape every architectural decision that comes next. Let's start with users. 300 million daily active users. About 20% posts on any given day. That gives us 60 million tweets per day. Now writes per second. 60 million tweets divided by 86,000 seconds in a day is about 700 tweets per second on average. At peak, say during a major live event, 3 to 5 times that. Call it 3,500 tweets per second at peak. Now reads per second. Twitter is read heavy. About 100 reads for every write. That gives us 70,000 reads per second on average, and up to 350,000 at peak, which means catching is not optional here, it's critical. Finally, storage. Each tweet is about 300 bytes of text. 60 million tweets times 300 bytes is roughly 18 gigabytes of text per day. Then add media. About 20% of tweets carry an image or video, averaging 2 megabytes each. That's another 24 terabytes of media every single day. Over 5 years, more than 40 petabytes. Which means we need a dedicated object store, not a regular database. Every decision from here is anchored to these numbers. API design. 5 endpoints capture the core feature set. First, post tweets to create a new tweet. Second, get tweet by ID returns the tweet and its replies. Third, get timeline, the home feed with cursor pagination. Fourth, post follow, to follow another user. Fifth, get search, to search across tweets and hashtags. 5 endpoints, 5 contracts between client and server. Here's the rule that protects you for the rest of the interview. Every single component we draw next must be justified by one of these 5 endpoints. If you can't explain why a service or database exists in terms of an endpoint, you probably don't need it. Before we draw the architecture, the conceptual flow of any request looks like this. And to load balancer, to API gateway, to a service, to a database, and the response curves back. Same path for every endpoint. Now let's build it for real. High-level design. We build it endpoint by endpoint. Starting with post tweets, this endpoint pays for the shared infrastructure every endpoint needs. The client, web, iOS or Android. The load balancer, layer 7, round robin. And the API gateway, handling auth, rate limiting, and routing every request. Plus this endpoint's own column, the tweet CRUD service, and the tweet database. Endpoint 2, get tweet by ID, search issue. Adds the reply CRUD service and reply DB. Why a separate service for replies? Scalability. A viral tweet can attract tens of thousands of replies. If they lived inside the tweet document, every fetch would balloon. Separate service, separate store. They scale independently. Endpoint 3, get timeline. Adds the timeline service and a placeholder timeline DB. We'll evolve this in Deep Dive 3 with Kafka and Redis. Endpoint 4, post follow. Adds the profile service and profile DB. The social graph lives here. Endpoint 5, get search. Adds the search service and search DB, Swamichi. Plus one final supporting service, Auth, Soundiest. Every endpoint delegates authentication to a dedicated Auth service. Tighter security, cleaner code boundaries, and easier to swap auth mechanisms without touching the rest of the system. And now the high-level architecture is complete. Every component earned by an endpoint, no floating boxes, no gratuitous services, each piece exists for a concrete reason. Quick recap. Requirements, core entities, API design, high-level design, all done. Now we make the system fast. Welcome to the deep dives. Deep dive 1, tweet, CRUD. For the database, MongoDB, a NoSQL document store. Tweets don't benefit from joins. Each tweet is self-contained. MongoDB gives us fast reads and writes at scale. For media, images, and videos, Amazon S3, object storage at massive scale. Never put binary files in a relational database. Now, optimize reads. 70,000 reads per second. Hitting MongoDB directly for everyone would be catastrophic. First, a Redis cache, popular tweets cached in memory after first fetch. Subsequent reads return in under a millisecond. Second, a CDN, a content delivery network. Static assets distributed to edge servers close to users. A viewer in Tokyo doesn't hit your Virginia data center. They load from a server down the road. If Redis fails, reads fall through to MongoDB. Slower, but the feature still works. Deep dive 2, search. Full text search across hundreds of millions of tweets in MongoDB would be unacceptably slow. We'd scan every document on every query. Instead, Elasticsearch, a distributed search engine purpose-built for full text search. It builds reverse indexes on tweet content, usernames, and hashtags. A search returns matches in milliseconds. Yerum, Fox Searchy. How does Elasticsearch stay in sync with new tweets? Change data capture, CDC. Every insert, update, or delete to MongoDB emits a change event. A pipeline propagates those events to Elasticsearch in near real time. If CDC lags, search is briefly stale, not broken. Deep dive 3, timeline. The most commonly asked follow-up in the entire design. How do we build the home timeline? Naive approach, fan out on read. User A opens their app, we fetch all the accounts they follow, query all their recent tweets, sort by timestamp, return the merged feed. Simple, but 1,000 database queries on every app open. At 300 million daily users, this does not scale. Correct approach, fan out on write. User A posts a tweet. It's written to the tweet CRUD service and simultaneously placed on a Kafka queue. Fan out workers consume from Kafka. They look up the author's full follower list. For each follower, they prepend the tweet to that follower's Redis timeline cache. When user B opens their app, no computation happens. The timeline is sitting in cache, pre-computed, served in under a millisecond. But what about mega influencers? 50 million followers, 50 million cache writes for one tweet would crush the system. The solution is a hybrid, under a million followers, fan out on write, mega influencers, flip back to fan out on read, fetch their tweets fresh, and merge them in at read time. If Kafka backs up, writes lag, but reads still hit the cache. Deep dive for profile. For user profile data, PostgreSQL, highly structured. Username, email, bio, profile picture, URL, join date, benefits from asset transactions. For follower relationships, SQL hits its limits. A social graph of hundreds of millions of users is a massive network of nodes and edges. SQL joins get expensive fast. Instead, a graph database, Neo4j, purpose-built to traverse relationships. Finding all followers, mutual connections, or people you may know is trivially fast. Authentication lives in a dedicated auth service that profile delegates to. Cleaner code boundaries, easier to swap auth mechanisms. Deep Dive 5. Security and observability, cross-cutting, applies to every endpoint. Authentication. Every API request validated through the auth service. Users must have a valid session token, SSH. Encryption at rest and in transit. HTTPS everywhere. Modern databases support native encryption. Enable it. Rate limiting. At the API gateway, IP-based. Cuts off DDoS attempts before they reach services. Short. Input validation. Every piece of user-submitted content, validated and sanitized. Prevents SQL injection and XSS. Never trust client input. For monitoring, Prometheus and Grafana, real-time dashboards, CPU, memory, request latency, error rates. For logging, the LK stack, Elasticsearch stores logs. Logstash ingests, Kibana provides the search UI. For alerting, PagerDuty fires notifications via Slack or SMS when anomalies hit. Sudden traffic spike, cascade of 500s, flood of failed logins. Here's what separates good candidates from great ones, articulating trade-offs. Your interviewer is almost certainly going to push back on one of your choices. 3 to think about. NoSQL versus SQL for tweet storage. We chose MongoDB. The trade-off, schema flexibility and high write throughput, but we give up strict, ACID, and complex joins. For tweets, self-contained, write-heavy, no joins, favorable trade. If tweets had complex relational dependencies, SQL would win. Fan out on write versus fan out on read. Write makes reads blazing fast but expensive on writes, especially for large follower counts. Read is cheap on writes but slow on reads at scale. Our hybrid is the production answer, but always acknowledge the trade-off explicitly rather than presenting one approach as universally correct. Microservices versus monolith. We chose microservices, more contents, independent scaling, deployment flexibility, fault isolation. The trade-off is operational complexity. More services means more infrastructure, more network hops, more places things go wrong. At Twitter scale, the benefits clearly outweigh. But in an early stage startup, a monolith is often the smarter starting point. Acknowledging that in your interview shows architectural maturity. Show that you've considered the alternatives. That's the difference between a passing answer and a hiring signal. What we deliberately skipped. Direct messages. The recommendation algorithm, ads and monetization, content moderation, notifications, fan out, analytics. 45 minutes is a starting point, not the whole system. Always call out scope. And there you have it, a complete production-grade design for Twitter. In under 18 minutes, we covered functional and non-functional requirements, back-of-the-envelope capacity estimation, a microservice architecture with a load balancer and API gateway, MongoDB and S3 for tweet storage, Redis caching, and a CDN for read performance, Elasticsearch with change data capture for search, fan out on write with a hybrid approach for mega influencers, a graph database for the social graph, a full security model, real-time monitoring with Prometheus and ELK, and the key trade-offs an interviewer will probe. If you're prepping for system design interviews, I drop a new walkthrough every single week. Subscribe so you don't miss them. All like takes 2 seconds and helps more engineers find this channel. Drop a comment. What company are you interviewing at? What system do you want designed next? I read every comment.